So we're very happy to have Conrad Wasko from University of Melbourne. So he's an ARC DECRA fellow there, and he's going to be talking about changes in rainfall and flooding across Australia. So Conrad, the floor is yours.
Thank you. So hopefully you can see my screen. I wanted to say, feel free to interrupt. I tend to get into my own world when I'm speaking. The presentation has about 40 slides, so it goes for like about 30 or 40 minutes. It's sort of in two parts. I want to talk about, I guess, rainfall, extreme rainfalls and flooding, and sort of how some authors have been looking at changes in those to climate change. And this comes very much from an engineering background. So the talk won't be particularly statistics heavy at all, I think. And so that's one part. And then the second part will be looking at flood timing. So that's the day of the year that floods occur. And there's just a little bit more stats there, but again, not much. Really looking at the applications of looking at trends for climate change. So to start off, I really want to give you a background for my approach. I did do a Bachelor of Science in statistics, but I never really, I guess I want to say I probably never really practiced statistics. I also did a Bachelor of Engineering, and I went on to work as an engineer for 4 years in flood hydrology, and then went to do a PhD in civil engineering. So for me, hydrology really is about the fact that we as humans, we have an impact on catchments in terms of the built environment. We build cities, we build drainage systems, we build roads, we build culverts which go under the roads to take flood flows and stream flows. We build dams for water storage. And it rains. And so as hydrologists, usually we're interested in trying to design for flooding and trying to withstand flood events. And the way this is done in engineering, and I don't know if you've seen these curves before, but the way that engineering design really begins, it begins by looking at these things called Ifd curves. So Ifd stands for intensity, frequency, duration. So on the x-axis, we have the duration. So the duration's increasing. So this is of storm or rainfall bursts. The y-axis, we've got the depth, and these curves are for different exceedances. So your 1% is what was commonly called before a 1 in 100 year event. And so if you're doing engineering design, you generally look at this curve and you say, oh, well, I have a small catchment, it'll probably respond to a 1 hour event. I want to design maybe for the 100 year event because there's some sort of critical piece of infrastructure there, and we go across here and it's okay, or whatever it is, say 70 millimeters of depth of rainfall over 1 hour is what I want to design for. So this is sort of the thinking that we often have in our trend studies. We really just want to know how extreme rainfalls are changing, how flood is changing for engineering design. And so we know with climate change, extreme rainfalls are going to increase. And this really comes from this Clausius-Clapeyron relationship. So if we consider the atmosphere to be a closed system, and there's some sort of equilibrium in the water in our system, so some of it would be in the liquid phase, some of it will be in the gaseous phase. As the temperature increases, there's more of the molecules in the vapor phase and the gas phase than the liquid phase. So as temperatures increase, the atmosphere can store more moisture, and then extreme rainfalls might increase. So there's a physical thermodynamic relationship which says as temperatures increase, we expect extreme rainfalls to increase. It's approximately 6 to 7%. Now, because there's a physical relationship, there's a whole suite of studies that have come out, and they started looking at rainfall temperature relationships in observations. And so the studies, I'm just going to take you through this now. Here I've got some sort of rainfall time series. This happens to be hourly, and I think it's for Sydney, and this is the temperature time series. And so what these studies do is they identify some sort of events, let's say maybe some sort of peak over threshold separated by some amount, and they match these rainfall peaks to some sort of temperature. Quite often it's, say, an average daily temperature. And you can plot these pairs and you can try to come up with some sort of statistical relationships, because we might be able to say something, well, if this is what we observe in natural variability, maybe we can use that analogously to infer something about how high temperatures might change rainfalls under climate change. So here we have temperature on the x-axis, rainfall on the y-axis. It's a logarithmic scale. And if we plot all the data for Sydney, we get a cloud of data like this. And so the first sort of paper that started looking at these temperature rainfall trends, or that made sort of a large impact, was published in about 2008. What the authors did was they binned the data. They found the 99th percentile of the rainfall in each of those temperature bins. And then they fit a curve through that and sort of tried to have a look at the slope and compared it to, say, a 7% line, or fit a line of best fit, but in essence, just trying to fit some sort of trend through those points to try and see what that relationship or what that increase in rainfall with temperature might be. And that's typically termed, for some reason, termed scaling. I don't think that's a particularly mathematical term, but that slope is called scaling. So my first paper for my PhD, so this was getting too long ago now, 8 years ago, was, well, actually, if we're interested in these relationships, maybe there's a statistical technique that we can use, and it was suggested by my supervisor, we can use quantile regression rather than this binning technique, because then we can get confidence limits quite easily. I mean, linear regression is a very simple statistical technique. So sorry, this is a quantile regression, so it fits to the extreme percentiles, but still very simple technique. It takes the linear form. And so just writing that paper and just applying quantile regression to this problem allowed us to use data sets a little bit differently. And I'm now just going to show you some results. And this isn't really about the statistics, but it just might be of interest to you from a climate change perspective. So this is some work that my PhD student Johan did. He's actually at the University of New South Wales. So this is Australia, based on the colours are the different Köppen climate zones, and the dots are our sub-daily rainfall gauges. And what he found was, so when we talk about scaling, we're just talking about that relationship with temperature. So by how many percent rainfall might increase with per degree increase with temperature. And so he used quantile regression, but did a bit more fancy things, making sure that any artifacts were taken into account in terms of making sure that we looked at the same storm durations and things like that. And so what he found was that actually these rainfalls, this is for, I think, the 95th percentile, for short durations, they do increase depending on the region. And then they increase less with increase in duration. And he found that trend consistently across all the climate zones. So for example, in the warm temperate zones where we have the most data, actually, you find that short durations are scaling around that, say, 7%, maybe a bit more, but longer durations tend to scale less the temperature. And it's sort of, I guess, observed variability with temperature isn't necessarily the best evidence for climate change impacts. So it's good to compare to other avenues. And so this is just to put things into some context. This is some climate modelling that was done out of the University of New South Wales. And what they did was they ran a climate model. I think it was a regional climate model, actually. And then they just looked at how much the rainfall has increased and divided by how much the temperature has increased as well. And they did find, indeed, rates of about 6% in the increases in the extreme rainfalls, or the 99th percentile. But they found for the 99.9th percentile, so more extreme events, increases in the order of 6 to say 15% per degree Celsius. So, in terms of a climate change signal, we have evidence to suggest that extreme rainfalls are definitely increasing with climate change, around that maybe 6 to 7% mark, but more extreme events might be increasing more than that. And indeed, quite long duration events, so when we talk to 1 to 2 days of length, they're probably not going to increase as much as 7%. So using that quantile regression, because it's so simple to apply, I could apply it to the entire globe. So this was using rainfall stations from across the globe. And in general, we find, sometimes you do find negative relationships, but in general, you do find these positive relationships in the order of 5 to 7% across the world for the rainfall. But what was really novel about this paper was not the changes in the rainfall, but it was actually that we applied this to stream flows as well. And I hope you can see the contrast quite clearly between those two figures. And although it's a very rough estimate, when we looked at the relationship for the 99th percentile between stream flows and temperature, we often found a negative relationship, which is contrary to the positive relationship in the rainfall. And so that was really not what we had expected, and really started to sort of kick off a lot of research for us, trying to understand, well, how might stream flows be changing under climate change, and why aren't they necessarily increasing? And so it led to us writing this commentary in Water Resources Research, which is Hydrologic journal, that talked about, well, if precipitation extremes are increasing, why aren't floods? And the hypothesis was something like this, that, well, if I have how extreme the event is on the x-axis, how rare the event is, and on the y-axis I have a sensitivity with temperature, well, extreme rainfalls are going to increase. And the more extreme the rainfall is, the more it will increase with climate change. And I think we feel quite comfortable with that. But for stream flow, and it depends on where you are in the world, but for stream flow in a lot of regions, these frequent events, they won't necessarily increase with climate change. And this is quite likely due to the fact that there's other things affecting the stream flow, like how dry the soil is before it rains. And it's only for these very rare events that, well, they just dump so much rainfall that these other factors that affect the stream flow response, they won't really matter so much anymore. And so the stream flow or the flood event will respond in kind to the rainfall event. I want to say that, an association with temperature is still not probably, it doesn't necessarily give a physical reason why things might be changing. And so I really wanted to prove to myself that actually these associations that we were finding were not just spurious. So we also looked at historical trends, and I only have 3 slides on this. It's very brief, but I just want to show you that this is actually these decreasing trends in frequent floods and increasing trends in extreme floods is actually something we've been observing historically across Australia. So there's a data set that is published by the Bureau of Meteorology, and they call it the Hydrologic reference stations, and it's daily stream flows. At the time of this study, there was 220 sites around Australia. They've expanded it now to about 460 sites. This is high quality stream flow that comes from catchments that are, as much as they can be, anthropogenically unaffected. So they don't have much regulation in them, and they can be, any changes should be able to be attributed to climate change. And what we did was, well, just as an example, this is just one catchment. We took average catchment rainfalls, and that was from AOAP. Rainfall, which is a gridded rainfall product across Australia, and we cookie cut average rainfalls using this R package. We also cookie cut for all the catchments the average soil moisture, and that is from another product by the Bureau of Meteorology called Aura-L, which is a daily water balance model, which models soil moisture across the entire continent. And you can see something that's quite nice. Well, you know, as it rains during, say, this season, catchment sort of starts to wet up slowly. And when there's no rain, well, soil moisture dries out. And this is the observed stream flow. And indeed, well, you only start to get a stream flow response when there's a fair bit of soil moisture in the catchment, and a large rainfall equals a large flow. So we sampled events as a partial duration series, on average 5 events per year. And I just applied again quantile regression just to try and look at how the more rare events might be changing. And I'm not going into details, but I aggregated all the data across Australia. I just pulled it all together quite the trends quite blindly. So I wasn't checking for independence or anything like that, but just to try and get some sort of ability to extrapolate out to more extreme events. So here I have the recurrence in years in terms of the annual recurrence interval. And here is the trend, and the units are different depending on the variable, but the trend is per decade. So yes, extreme rainfalls do tend to increase on average across Australia. There's a lot of variability in rainfall trends, but the more extreme the rainfall, the more likely it is to increase. So that was nice to see in our historical trends. And the stream flow, indeed, on average across Australia, frequent flows have not been increasing. They've actually been, by frequent flows, I mean your 1 in 2 year, say, so frequent flood. Frequent floods haven't been necessarily increasing. And it's only these most extreme events, so say your 1 in 10, 1 in 40 year events, that actually have been increasing with climate change. On average, we found that the soil moisture before it actually rained has been decreasing. So catchments have actually been drying out on average across Australia. So that quite likely has a large modulation effect on the flood response. The other thing that's not shown here, but also in other work that we've done, we've also shown that the storm volumes have also decreased. This is only looking at the big bursts within the storms. So although these percentages might seem quite small, 2.5% per decade, well, look, if you divide that by an average temperature increase of 0.2 degrees per decade, well, that's actually corresponds to an increase in rainfall intensities of 12.5% per Celsius. So the point here is that extreme rainfalls are likely to increase at much more than the rate that the Clausius-Clapeyron relationship gives us. So we are, as engineers, we are worried about the increases in extreme rainfalls, and we do want to be able to quantify them to come back to those Ifd curves in order to be able to design infrastructure for climate change. So that sort of ends that first half of the presentation. And the second half, I'll talk a little bit about flood timing. And the reason why I got interested in that was, again, I was curious to see if there was any response or signal that we could see due to climate change in the flood timing. And the flood timing is just simply the day of the year that you expect to see a flood on average. So the annual maximum stream flow, the day of the year that you expect to see them. So a really trivial example, because most of these studies use circular statistics. And so if a flood or annual maxima, so when we talk about floods here, we're always going to be talking about the annual maximum, the day, the largest stream flow in the year and that corresponding day. Well, if you say that a flood occurred on the 31st of January in one year and the 1st of January the next year, if you use linear arithmetic statistics, then quite clearly you're adding 1 plus 365. You divide those by 2 and you get an average which is in the center of the year. And you know that that's nonsensical. Indeed, you know, really what's happening is that the floods generally occur around the start of the year. And if you transform your data into the circular space, well, and you calculate the circular mean, then indeed you'll get a value which reflects that. So all you're trying to do is when you have the day of the year, you're just dividing it by the number of days in the year. So say the flood occurred on the 100th day of the year, and you divide it by the number of days in the year, and you multiply by 2 pi, and then we have something which is in radians. And so there's these formulas here which give you the mean in the circular space. And there's also a strength of the seasonality, which is described by this statistic. And it's sort of akin, I guess, me as an engineer, sort of akin to a variance, though it's not called that. It's called the resultant length. And when R is 1, it implies that all values coincide. So they're all really, really close together and really bunched up. And 0 implies that they're pretty much spread across the uniform space, or possibly antimodal. So R equals 1 is bunched up, R equals 0 is more spread out. So what do these statistics sort of look like? And again, we're interested in flood timing. So this is just one particular catchment. And these are the annual maxima floods in blue, and their size, so how big the flow was, is given by the size of the circle. So you can see that, well, the seasonality sort of corresponds to around this August month for this catchment. You can see that the R of the flow is quite large, quite close to 1. So the grouping is quite squished together. Generally, our floods occur around the same time of the year. You can see that the rainfall, which is in orange, it's more spread out. So the R is lower. So rain is more likely to occur maybe still probably in these more winter months, but not necessarily corresponding as closely as the stream flow. And you can see the antecedent moisture conditions, the timing, so the maximum antecedent moisture conditions in the year, they actually follow quite closely the stream flow. So we're sort of seeing that the maximum soil moisture coincides very well with the maximum flow, but not necessarily to the maximum rainfall. So we can look at maps around Australia to characterize this seasonality. And so this is for the rainfall, and these are, remember, this is annual maxima, but it's nice because sort of the annual maxima tends to reasonably follow mean rainfall seasonality. So in the tropics, we have a very strong seasonality indicated by these dark blue dots. The R is close to 1, the resultant length. And generally the annual maxima occur, let's say maybe towards the end of the wet season, but sort of in your sort of February months. Around the southwest of Australia, we see a very strong seasonality towards winter. So generally annual maxima occurs in winter. But what's interesting is around, I guess we're probably used to the fact that it's sort of quite overcast during the winter in Victoria, but actually there's no real strong seasonality here. And so those greyed out dots, or the ones with the grey outlines, are not statistically significant. So actually extreme rainfalls or annual maximum rainfalls can sort of happen at any time of the year. I mean, we still have to get a number based on our formulas, but really there's no strong seasonality of the annual maximum rainfall in Southeast Australia. For the annual maximum soil moisture, well, it tends to peak probably towards the end of the wet season in the tropics. That sort of makes sense, I think, and peaks in the end of the winter months in the southern parts of Australia. And this seasonality now is quite strong. And so maybe you can see where this is going, but there's sort of a theme here where the soil moisture is an important modulator of the stream flow. So the next figure shows stream flow maxima. And indeed, we have these peaking streamflow maxima do tend to peak towards the end of the wet season in the tropics, and indeed towards the end of the winter months in the southern parts of Australia. And you can see that this seasonality seems to correspond very well to the soil moisture seasonality. Now, this isn't necessarily a cause and effect thing. I mean, they both affect each other, but it's just interesting to note that the rainfall seasonality doesn't necessarily, of the annual maxima, doesn't have to necessarily correspond to the streamflow annual maxima. So I'm interested in climate change, so I'm interested in the trends. This is just a lower smooth of all the sites. So this is for Southwest Australia. So I've just plotted now a time series of all the sites and just trying to see if there's some sort of relationship. And there's a lot of variability in this, but I think it's fair to say that in the southwest of Australia, it looks like the seasonality is tending towards later in the year for all the variables for rainfall, soil moisture, and streamflow. And you can see that the flow actually tends to peak after the soil moisture peak, and doesn't really bear much resemblance to when the rainfall maxima occur. So you can see that clearly the soil moisture has a very strong modulating effect here, where it takes time during that wet season, during the winter, for the soils to wet up before you actually get your annual maximum. In the central north, so we're looking at now start of the year, seems to be a trend to earlier flooding or earlier soil moisture maxima and earlier rainfalls. Again, now the soil moisture seems to be peaking after the flows. So indeed, okay, it's large flows are likely corresponding to cause large or wetter soil. So there's the feedback between the two. And in the southeast, well, what we sort of described is true here. There's no real trend in, I mean, you can't find a trend in the rainfall seasonality because there isn't one. So if the rainfall seasonality is roughly uniform for the annual maxima, then we're not going to really see a trend. I had to plot this on some sort of axis, but really there's no trend here in the circular space, you can imagine. But the stream flow and the soil moisture do have a very strong correspondence. There seems to be something happening here where there seems to be some sort of change towards earlier stream flow and soil moisture maxima, but you know, there's not that much data to really support that there's a strong change. Now, what we can do is we can actually formalize these relationships using circular regression. And the reason why this might, again, this might seem quite trivial to use circular regression for this problem, but most authors don't use circular regression. They use ascent slope. And ascent slope doesn't work in a circular space. They use ascent slope in a linear space. And so if we're looking at trends in a circular space, I think we should be probably using the appropriate technique. So we use circular regression in this paper to look at trends. What's interesting to note is probably that none of the trends actually came out to be statistically significant. So we're really struggling to find strong trends in any of the variables. So this is the stream flow. Probably is a shift to later flooding in southwest Australia, which is what it looked like when I showed you those time series, and probably earlier flooding in the tropics, but very mixed results elsewhere. And the rainfall, again, here, you know, well, the circular regression has to find a trend. I mean, if you put in some numbers, but you know, the trends are not statistically significant, and you know that there isn't a strong seasonality in southeastern Australia, so these results don't really mean that much. But in the tropics and in the southwest Australia, well, maybe these trends actually do mean something, because we have a strong seasonality in these regions. So maybe we are seeing shifts towards earlier extreme rainfalls in the tropics and later extreme rainfalls in the southwest of Australia. And again, I just want to note that, well, the trends in the soil moisture, you know, they sort of look the same or similar. And we can plot these trends as a scatter plot just so that our eyes can go to maybe what we want to see. And here I only plot values where the R, or the resultant length, is statistically significant. So we know we've got some sort of strong peaked seasonality. So here we have the rainfall trend for all the sites on this axis, the soil trend for all the sites on this axis, flow trend, and rainfall trend. So here the rainfall trend and the flow trend, when we plot the trends against each other, they don't actually have terribly a lot of correlation, 0.3. There's some correlation there, but it's, if you do an R squared, well, you square that value, so it's not really very high. But the correlation between the soil trend and the flow trend is relatively strong, about 0.6. So we can see that at least where there are trends, the trends, whether it's shifting to earlier or later in the year for the stream flow, they seem to be shifting more along the same lines as what the soil moisture trends are, rather than the rainfall trends. So really, some take-home messages from this, and this sort of looks like this is my last slide, but there's a little bit more to come. Just some take-home messages here. The timing of the stream flow annual maxima is actually more closely linked to the timing of antecedent soil moisture than the rainfall maxima. So what I've been harping on about, that the timing of the soil moisture matters. The more extreme the flood event, the weaker the dependence on antecedent soil moisture relative to rainfall. So if a really large rainfall occurs, you're going to get a flood, and the soil moisture conditions probably don't really matter. And so using circular regression, stream flow annual maximum timing is found to be non-stationary. Although it wasn't significant, we definitely found regional coherence. Now, trends, maybe if we pulled our data together regionally, we would have found statistically significant trends. And it looks like those shifts are consistent with the shifts in soil moisture. So I did say that a lot of studies, like we use circular regression, and a lot of studies don't. They use ascend slope to look at trends in flood timing. And this was sort of, I must admit this was bothering me, and I didn't really know why. And so I started to dig a little bit deeper, and in the end, with much difficulty, and I mean a lot of difficulty, we managed to publish this paper. And there's a good reason why we had difficulty publishing it, because we're sort of suggesting that you might not need to use circular statistics for this work. And I appreciate that's, like, why are we going back to linear statistics? But there's sort of just an interesting thing that happens with flood timing, in that it's one of the very few variables that we encounter in hydrology that actually has a normal distribution. So I'll go into that. And it's just a curiosity, but it's something that I think is really quite cute that Rory observed, and so we published. So going back to our trivial example, okay, we know we can't use linear statistics if you've got a break between your calendar years, right? So we're not going to sum up the last day of the year and the first day of the year. But it turns out that there was this paper published in a long time ago now, 70 years ago, and it said, well, if a circular variable does not extend around the circle, it can be linearized without great error and can be analyzed based on normality. Now, why this is interesting is because if I did a really extensive literature review, and when you trace all these flood timing studies back, they all just say you have to use circular statistics, and no one ever really checked whether you could actually just linearize the variables. So that was really interesting to me anyway. And so if we look at trying to linearize the data, well, what I've plotted here is the month of minimum stream flow. So we can linearize the data if we start our analysis on the year that on the month that has the minimum stream flow. Okay, so here's just a figure of what that minimum month looks like, and I appreciate there's sort of a lot to digest here with the colors, so maybe we'll just look at Australia. Well, in the monsoonal tropics, the month of minimum stream flow is in the winter months, and that sort of makes sense. And if we have sort of more winter dominant stream flow in the south of Australia, which we know, then the start of that water year, or the minimum stream flow month, will be in the summer months. And so that can become a starting point for us to linearize our data. So what does this look like in practice? So this is a site in the tropics. This is the flood timing from the time series, right? So got quite a long time series. And so these are the number of times that the flood maxima has occurred on these days. So you can see generally it occurs in January, February, March, but sometimes in December. Now, sure enough, if you take a linear average of this, well, it's biased towards these occurrences towards the end of the year. And if you take a circular approach using circular statistics, then this is the true mean, the one that's the filled circle. What you can do is you can standardize on that month that has the lowest amount of stream flow, which occurs somewhere around here. And so you get something like this. And this actually, you can see it sort of looks like a normal distribution now. It doesn't span across the start or end of the year. And so arithmetic and circular means are the same. But what's really cute is actually if we plot this as a QQ plot, it looks really, really normally distributed. And so we can just perform a hypothesis test on whether the skew is zero or not to try and see if our distributions are normal. And you can see that actually at most sites around the world, particularly, so 80% of sites, but particularly in the southern parts, southern hemisphere, we can actually approximate our data as normal. So it was just a really, I think, acute finding, and a throwback to the fact that, well, you can actually use parametric statistics for a lot of this analysis if you want, and you don't have to necessarily go down the line of all these complicated or more complicated equations. For engineers, those equations are complicated. I'm an engineer, so I can say that. So looking at some trends, and this is now just using straight out a linear regression or a sense slope. The results are pretty much the same. A lot of variability in our trends across the world. Earlier flood timing in the southern parts of Europe, later timing in the northern parts of the UK. This has been shown by other studies, so I'm quite confident in these trends. These trends here sort of correspond to what we were showing before using the high quality Australian data, earlier flood timing in the tropics, later in the southern parts of Australia. But there's just one last point that I need to make, and this is what was bothering me from before, that, well, I sort of was advocating for circular regression to look at trends. And I said a lot of authors use sense slope or linear regression, and that's okay, but they don't actually standardize on the water year. So although you can use circular statistics to calculate the mean, the circular mean, which is what most studies do, and that's fine, then when they're looking for a trend, they still analyze, you have to pick some sort of arbitrary start and end point. And so they pick the calendar year, and you end up with this situation that, well, let's say this guy increases. So let's say the flooding in December decreases. Now, is that a shift to flood timing that's later in the year or earlier in the year? And so if this is how you standardize your data, you will find that the shift is towards later in the year, but that's not really representative of what's happening, because we know that really this guy should be sitting here, and the shift is towards flood timing that's happening earlier in the flood season. So it's really important to always standardize your hydrological data on the season of rainfall, flooding. And indeed, if you look across the world, what we found was that there's a lot of sites where the trend would be miscalculated if you didn't standardize properly. So 35% of sites. So you don't have to go down the path of this circular regression, but even the existing studies, if they were just using sense slopes, because they didn't standardize on their data, they still might have misclassified the direction of the trend. So that is all I had to say. I appreciate there's a lot going on there, but I hope it wasn't too heavy for a Friday afternoon, and very happy to take questions.
Thanks very much, Conrad. It was a really interesting talk. Are there any questions for Conrad? Yeah, Boris, do you want to go ahead?
Hey, Conrad. That was great. There was a lot of stuff, but it wasn't too much for a Friday afternoon. It was good. I have maybe two quick questions. I guess the first one is maybe more related to the first part of your talk. But do you consider any spatial extent to these things in general, or is it mostly point-wise and you don't look at dependence in space?
Yeah, that's a really good question. So me personally, I haven't. So I'll probably give a long answer. So I just looked at always point data or catchment average data. But there is like a paper by, there is a paper by Scott Sisson and Seth Wester, and they use this max stable approach where they actually consider the spatial dependence to try and, I think, increase, I guess, the power of the sample. So that's one way of doing it. And the other one in hydrology is often this regionalization where you essentially just, pull the data and you make sure that your region is homogeneous. And that's often used for regional flood frequency analysis. So the answer is I haven't, but there are definitely methods out there which, have been shown to be really, really beneficial.
So does that mean that you believe that it wouldn't make too much of a difference?
I mean, yeah, that's a good question. I think my sort of opinion is probably if I look at, but this is just my opinion. If I look at something like this, I'm like, oh, well, okay, so none of those trends were statistically significant, but given that a lot of sites showed the same direction, I'm fairly confident that it's a real thing. But yeah, I think, although I want to say that maybe the conclusions wouldn't necessarily change, I'd say that I'd probably find a lot more, my conclusions might be more robust if I did actually use some sort of regionalization method or consider regional statistics. Yeah, so I think conclusions might not change, but I think they'd be much more robust if I did go down that path.
Yeah, I guess they might just be harder to implement. That's probably one of the hurdles.
Yeah, but it's sort of a I think one of the authors on that, the reviewers on the WRR, that last paper, made a good point that, well, I mean, for me, I don't think I'd be able to code up a max stable approach, but there's an R package out there. It's coded it up, so yeah, I personally often think that, I just wanted to say, what's hard is, I personally would find it hard to maybe apply, but I mean, yeah, other authors might be, much more confident to jump in with those things. Yeah,
I agree. It's probably not so easy, even for an expert. I don't think it's super easy to implement these things.
Yeah, so, that's very kind.
Yeah, and the other thing I was thinking, it was towards the second part where you had the map of the world, and then you had the different month and different colors for the month.
Oh, yeah.
And I was thinking, I mean, because the color is just the month, it doesn't reflect the season. So, is there, if you would care about the season, because, the first month is January, right? That's what you consider everywhere in the world. But it's not necessarily going to be a summer month everywhere. Like, take Europe or US, and then it becomes a winter month. So does that change a bit if you were considering, I don't know, resetting the kind of the clock from 1 to 12?
Yeah. So I think, I mean, I want to say there's two things. One is that, like, yeah, when you do reset, it becomes sort of, there's an arbitrary choice of what direction you go, whether you sort of go forwards or backwards. So that's one thing. And the other thing that, not sure if this is quite hitting the question, but yeah, I want to say that this isn't the only definition of a water year that's out there. I think it's, personally, I think it's probably the most consistent one, but some people sort of use things like, well, the minimum of, you know, moving average of six months or something like that, to really try and, because I could be, you know, like when I showed this, I mean, I showed an example which standardized quite nicely and then was nicely peaked here, but sometimes these things will still sort of, I'll still have some small trails, you know, that cross the start and end of the year. But as a general rule, it seems to work reasonably well, and thankfully flooding tends to be quite constrained because of the season usually. But maybe just of interest, and it's something to worth pointing out, that so in places like here in Northern America, the flooding tends to be quite, there's two things that happen. One is that because of the snowmelt, there's a large tail in when flood events occur, and there's also a bimodality because they occur, one, due to snowmelt in that spring season, but they also occur often due to just really high rainfall events during more sort of end of the summer months. So you also get these bimodalities, and so at that point, want to say that the standardization, you know, other authors will argue that you should use sort of more non-parametric methods, and really should just be looking at the data at that point. That was sort of a long-winded answer.
Oh, that's good. I like it. It's I like your last example. That's great. Thanks, Conrad.
Thanks so much. Thank you.
Are there any other questions? All right, if there are no further questions, then please join me in thanking Conrad for his very interesting talk. And I hope you have a good weekend and see you next time.
Thank you.